As a supplement to the content in this chapter, I'm going to take you through building out raw hexadecimal transactions in GoLang in this section of the course. And I'm going to do that using the libsv libraries. They're supported by Bitcoin Association and some prominent Bitcoin SV companies. And it's just a little program that you can use to construct transactions. And then once you construct them, we're going to do it with testnet transactions, and I also have a local reg test environment running, so I'm going to post the raw hexadecimal to that reg test environment and show you what it looks like, show you what this looks like in action. Now, there are a couple of caveats to this. Number one being we're not doing this in a secure way. We're not going to be generating new addresses every time we send a transaction. We're going to be reusing the same address, which you definitely don't want to be doing, but it's just to give you an example of how this works and what a Bitcoin transaction looks like and kind of the process behind it. So jumping into my command line here, I've gone ahead and pre-generated some addresses in wallet import format keys, some WIFs. Here's Alice's address and then her change address. Here's Bob's address and then his change address. And then I also have the reg test stack here running, and I can just do a Docker container ls just to show you that. Now, before we actually jump into the program here, I'm going to just fund Alice's address so that we'll be able to send some Satoshis from it. So I'm going to take her address here, just copy it, and then the reg test environment, the reg test stack here, comes with a little script that we can use to access the Bitcoin CLI within the container. So we can just do regtest.sh, and then we'll go send to address, and we will copy the address, or we'll paste the address that we're sending to, and let's send like 40 BSV. And so once we do that, that's going to generate our transaction here, and then the next thing we have to do is just do a block generation here. So if we do generate one, that's going to generate our block, and then I'll just bring you over to the What's on Chain API that's running here, and let's refresh this. And so you notice that once I refresh that, the next block, or the most recent block, has two transactions in it. That's because it contains the transaction that we just sent. And so if we jump into the block here and then we jump into the transaction, you'll see it listed here. So this is that new output that was generated. And let's go have a look at that, and we can have a look at the JSON. And so you'll notice here that transaction ID matches the transaction ID that we were just looking at. And one thing I should just note here, the libsv GoLang libraries are using these addresses in Big Endian, and if you're a little bit confused with what I mean by that, Big Endian, Little Endian, it's just the way the bytes are ordered. So a lot of computer systems use Little Endian, like Intel x86, and most of the main processors use Little Endian to process inputs. And essentially what it means is that just instead of this string being ordered this way, this string of hexadecimal bytes being ordered this way, this byte here would be at the front, and then this byte would be there, etc., etc. It just reverses the order of the bytes. But a little bit of a unique situation with Bitcoin. It's kind of interesting how the endianness of transaction IDs and block IDs were decided. So if you look at the output of a hash, the hashes that are used in Bitcoin, SHA-256 and RIPE-MD-160, so the output hash of SHA-256, which is used for generating transaction IDs and block IDs, is 32 bytes long. And so that is much longer than the 8 bytes that computers, or 64-bit computers, are able to store as integers. And so you can use big ints, but really the output of a hash isn't a big int natively. You would have to cast it as a big int. You'd have to convert it to a big int. And so there's a bit of a debate on how you denote the endianness of a hash output, and there isn't really a right way and a wrong way to do it. Generally, you would consider it big endian, but the way Bitcoin does it, that the output of those double hashes, particularly the transaction ID and the block ID, are considered little endian. And so you'll see it's actually being displayed in big endian here, but I'll show you once we generate the hexadecimal of the transaction, it's actually represented in little endian, like we talk about in the chapter. And so not to go off on too much of a tangent here, but interestingly, the creator, Satoshi Nakamoto, Dr. Craig Wright, he said that the reason why he chose to denote the output in little endian was so that it has a unique way of forming this. It's a unique way of building the transactions. It makes the system unique, and because it makes the system unique, it makes it patentable. And so if he were to follow main conventions of using just big endian values, then it wouldn't be as patentable, and he wouldn't be able to protect his intellectual property and protect it from patent trolls, etc. So kind of an interesting little tidbit there. And if we jump back into our command line now, let's have a look at the code. Let's have a look at the program. So this is just a really simple GoLang program that I put together using the libsv libraries. And all it's doing is it's going to be taking in the necessary inputs needed to construct a transaction, and then it's going to construct that transaction and spit out the raw hexadecimal of the transaction. So you'll notice here I have the imports needed for this, some buffer stuff. That's mostly just for input output. And then here are the libsv libraries that it's using. Go Bitcoin keys, Go Bitcoin transactions, version 2, and then version 2 unlocker. And so if we just jump into it here. So all this program is doing is it's going to be asking some basic command line interface questions to get these details needed to build this transaction, and then it's going to build a transaction. So that's basically what it's doing. It's starting out with using the libsv library. So Bitcoin transaction, we're going to create a new empty transaction here. Actually, the first thing it's doing is asking how many input UTXOs, how many UTXOs are going to be funding this transaction. Then it's building a new transaction object, essentially, or struct. And then it's generating an empty array of the wallet import format keys needed. And then this is just a conversion for integers. And then it's asking the funding UTXO or the transaction ID. Like, these are all the details. So you have transaction ID, and then the index, which is the vout, the script, which is the unlocking script or the locking script, and then the value and the wallet import format key needed to unlock it. So let me just bring up what's on chain again, and we can have a look at those values. So transaction ID, this is it here. And then we needed our vout or vin, but it's the vout of this transaction. So when you think about it, whenever you create a transaction, you're creating a new output from that transaction, and that new output has a locking script, and you're locking Satoshis into that output. And then what you're doing when you're spending that is you're taking that output from the previous transaction and you're using it as an input to your new transaction. And so what we need to do is we need to look at that previous transaction and get the details from it. So we need the transaction ID, we need the vout, we need the value of it, how many Satoshis are being stored in it, and then we need to be able to unlock it. We need the proper key in order to sign it or provide the public key hash in order to unlock it. So jumping back into the code, if we have a look at this again, what this does is it allows us to, this is just running a loop. So first we're asking how many of these we need, or you can have basically as many UTXOs, input UTXOs as you want. So it's just asking how many we're going to be using, and then it's just needing details of each of those, and it's just populating them into these variables here. And then once it's populated into the variable, it is just creating that input using this function here. So this is the transaction. Remember, we created this transaction object, and then this transaction.from method or function allows us to add this input. So it's just doing that, looping through that. And then similarly, if we jump down a little bit here, we're doing the same thing for the outputs. And so these are the new UTXOs, the new outputs that we're constructing in our transaction. And so we're getting the number of those, and then we're doing another loop here, and we're just creating those outputs. And this is where our to address is going to be. This is where we're going to be sending the Satoshis to. I guess it's not really right to say sending the Satoshis to. It's more like, what are we going to be? We're transferring ownership of them. Which key are we going to be associating with them, or which identity or pseudonym are we going to be associating with them? We're transferring ownership, and when that transaction goes onto the blockchain, when it gets timestamped, that's what it's representing. It's essentially a contract between two parties, or two or more parties, I should say, and it's a time-stamped digital signature. It's a time-stamped contract of a transfer of ownership of those Satoshis. And those Satoshis are properties. So once you have that contract or that action signed and time-stamped, you've transferred the ownership of those Satoshis from one individual to another, and they're able to access that and do the same thing again using this process. Or there's other ways to do it, but obviously we're just doing this with a standard transaction. This is the most well-known way to do it, so it's an easy way to explain it, but that's what's happening. So it's not really like you're sending it from an account to another account. It's each UTXO represents a new contract between two or more parties transferring ownership of Satoshis. And so jumping back into the code, or keep going in the code here, so just like we did with the input UTXOs, we are adding our output UTXOs to the transaction, and then once we've done that, we're adding our change address. So a good analogy, or a good way to think about this, is each UTXO is like an envelope. And once you've licked the envelope and you've stuck the envelope, you've closed it up, and you've sent it off, the person that's received that envelope, you could say that's a UTXO, once they rip it open, that envelope can't be used again. So every time you spend a UTXO, you have to take the entire contents of that UTXO and move it to new envelopes. And so that's why we use this change address here. So this is a second UTXO essentially, is what we're adding here. So we have our primary UTXO, which is going to be Alice, or which is going to be Bob, essentially, because we're sending from Alice to Bob. But this change address is actually going to be Alice's change address, because she doesn't want to send the entire contents of her UTXO to Bob. She just wants to send however much she wants to send to Bob, and then she wants to store the rest of it in a change address so that she can use it again. And so once the change address has been entered, then the final step here is to go through each of the input UTXOs and actually unlock them. So they need to be, the unlocking script needs to be provided to unlock them so they can be spent. And then once that's done, then the transaction is essentially created, it's complete, and we can print out the raw hexadecimal. And then this is just a helper function to send output to standard out and get that input, that required input that we need. And so let's go ahead and run this. So if we just exit out of NeoVim here, this is the directory that we're in. We can just go run, and we'll go multi-transaction example. And so we only funded one UTXO at this point, and so we only have one UTXO to use. And the UTXO that we funded was Alice's UTXO, so we're just going to say 1, and then we need to enter the information needed here. So if we pull up that transaction again, we can just gather this information. So the first thing we need is the transaction ID. So we'll just copy that over. And then the next thing we're going to need is the index, or the output index. So that's here in vout. If we scroll down, we know that we sent 40 BSV, and we know what our address was. Following that, we're going to need the locking script, but let's copy over our transaction ID first. So we'll just go back here and we'll paste that in. We know our index is 0. And now let's get the script. So if we bring this back over here, now we'll look at the script, and this is just this locking script in hexadecimal. That's all this is. And so we'll copy paste this. And then we needed the value and our wallet import format key. So let's head back here. We'll paste this in. And then we need our value, which was 40 BSV. And we know that 1 Satoshi is 1 times 10 to the 8 BSV. So we'll go 40 and then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then we need our key in order to unlock this UTXO. And so we'll just copy over Alice's wallet import format key here. We'll paste that in. And so now we've provided our input UTXO. And if we had specified there was more than one input UTXO, this would loop again, and we would input the same information for the other UTXO, but we just have one UTXO in this example. So let's continue on here. So we'll generate one new UTXO. We're going to be generating two because we're adding a change address, but let's just generate one for now. We'll make that Bob's address. So we'll say 1 here. And then it's asking for the address and the number of Satoshis that we're going to be sending. So let's copy Bob's address here. Oh, that's Alice's change address. Let's copy Bob's address. And then we'll specify the number of Satoshis we're going to send. Let's just cut it in half, and we'll say we're sending Bob 20 BSV. So that's 20, and then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. When we press enter, then it's going to ask for the change address. And so let's look at our little list here, and we'll get Alice's change address, and we'll just copy that, and we'll paste that in. And now we'll go ahead and press enter, and we get our output transaction in hexadecimal. We get our raw hexadecimal transaction. And so what this is it's all the information that we just entered in hexadecimal format. And so what we're going to be able to do is we're going to be able to take this, and we're going to be able to, using our Regtest environment, like obviously you can do this in different ways. And if you were using a mainnet, you would post this to some kind of an API, or you could use the merchant API to post this to a Bitcoin node, or eventually you would be sending something like this maybe to an SPV node or something like that. But essentially, this is our transaction. This is our envelope. And it doesn't matter who sends this envelope to the network. In our case, it's just going to be the Regtest network. But anybody can send this to the network. And once it's sent to the network, once that information is timestamped to the network and that UTXO gets spent, it's validated, etc., then that gets added, and it doesn't matter who has added it, that gets added to the chain. So there's kind of an interesting little point that I want to go into a little bit there. And that's this difference between a UTXO model of doing things versus an account-based model. And so we're not sending things from somebody's account to another person's account. We're not saying this person started out with this much BSV in their account. We're subtracting that, and then we're sending it over to this person. We're adding it to their account. That's not what's happening here. What's happening is we have all of these Satoshis that exist on the chain, and we're transferring ownership from one individual to another. And we're not actually transferring the Satoshis themselves. We're transferring ownership of them through a contract, through digital signatures. And that's a really important distinction to make, because it's really, really fundamental to how Bitcoin works in general, how BSV works, how it's secured, why it's able to scale, why SPV works, why it's going to have the capacity to add all kinds of new things like a micro transactions economy. It's all of this comes from UTXOs and the small world network design and everything else. It all comes together to form this network. So the other thing I just want to quickly point out, if you remember our transaction ID, it's listed up there too, but I'll just paste it here. It looks like that. And I should just clarify, it's not the transaction ID, it's the previous transaction ID of that input UTXO. But if you remember from the chapter, so the first 4 bytes are version 1, 2, 3, 4, and then following that we have the number of inputs, and remember we only have one input, and that's another byte there, that's 1. And then this is our transaction ID right here, like this. And remember how we talked about in the raw hex, it's in little endian form. And so that's why those bytes are reversed. And so you'll see the 0A byte here when it's in Big Endian on the Block Explorer, and the nodes treat them like this too. It's that 0A is at the front here, and then that BA was at the back, whereas in the transaction it's in Little Endian, so we got the BA here, or B8, sorry, I should say, and the 0A here. But then what we can do is we can just copy this entire thing, and then we'll jump on over to our reg test environment here, and we'll go reg test, and we'll go send raw transaction, and then we will just paste this as a string, and we'll press enter, and there we go. It's generated our transaction. It's posted it, and so that's the transaction ID in Big Endian. And then we just have to generate one more block in order to see it. So we'll do that. And if we pull the Block Explorer up again here, we'll just jump back to the home page. We'll see that our transaction was just generated. So let's jump into that block, and we'll jump into that transaction. And there it is. So there's Bob's address. There's Alice's address. Alice is the input. And there's Bob, and then there's the change input. There's Alice's change address. We look at the JSON. There we go. So we just sent our first transaction. And then from here, now that Bob's address is funded, we can have him send something back to Alice. So let's go ahead and do that. So jumping back into our command line here, we'll just clear that. And we'll run our program again. Oh, here we go. No, let's just do this. Go run multi-transactions example. Okay, so we need to enter the number of funding UTXOs, and Bob's only got the one address funded right now, so we'll just go 1 again. And then we need to gather our information here. So if we go back to our Explorer, we need our transaction ID, our index, our script, our value, and our WIF key. So we'll pull this back up again. There's our transaction ID, and that's in Big Endian. We'll just copy that. And then we needed our transaction out. So remember, this first one here, we sent Bob, there's Bob's address. We sent Bob 20 BSV, and then we sent the change to Alice's change address. And so this is Bob's address, this is our funding address, and that end value is 0 again. So we'll jump back here and we'll just paste those two values in. So paste, and then we'll go 0. And now we need the locking script here. So let's pull this back up, and there it is in hexadecimal. So we'll copy that as well. And then we know that the value of it was 20 BSV, so 20, 1, 2, 3, 4, 5, 6, 7, 8. And then we need Bob's WIF here. So we'll go back to our little list here, and we'll just copy and paste that. And now we want to generate new UTXOs. Well, let's stick with 1 again, and then they'll both have change in this afterwards, and they both have change afterwards, which we can then send 2 next time. So we'll do one more example after this, sending 2. So we'll stick with 1 for this one. Okay, so 1 UTXO, and we'll be sending it back to Alice's address here. So let's just copy that. Copy that over, and we'll paste it. And then how many Satoshis do we want to send? Let's just cut it in half again. So we'll go 10. So 10, 1, 2, 3, 4, 5, 6, 7, 8 Satoshis. And then Bob's change address. So Bob's change address is right here. Let's copy that and paste that in. And then we'll hit enter. And there is our raw hex for our transaction. If we copy that, go to our reg test here, and we'll just go send raw transaction, and we'll paste that in. There we go. There's our transaction ID, and then we'll generate one. There we go. And so pulling our Block Explorer back up here, go home. There's our transaction. Let's just go into that. And so you'll see this was just the Coinbase there. and we'll jump into the transaction. And here we go. So we have, this is Bob's address now, and we're sending to Alice's address. We're sending 20, we're sending 10 from 20, and then we're putting the rest into Bob's change address. And we can just jump into the JSON and have a quick look at that again. You'll see that there's our outputs, 0, 1. There's the values, got our transaction ID. All the stuff is the same, but just with different values. And so for our final example, I'm just going to pull this back up again actually, and we'll open this up in a new tab. So this is our most recent transaction that we did, and we funded Alice's address with 10 BSV. And so if we go back here and we find that transaction that had the first transaction that we did, we were sending 40 to 20. This is Alice's change address here because we're going to need that. So what we're going to do is we're going to send from Alice, we're going to send back to Bob, but we're going to use Alice's address plus the change address, and we'll come up with a new amount of BSV to send Bob, amount of Satoshis. So we'll just put this aside for now, jump back into our command line here, and we'll run our program again, go run, multi-transaction example. And so this time, instead of entering 1 for the funding UTXOs, we're going to enter 2. And now we're going to gather the information that we need. So we'll pull up our Block Explorer again. And so this was the most recent one we did. So let's copy this transaction ID. And we're sending from Alice. And so we know that we funded Alice 10 last time. This is her address. And so she was vout 0 again. And then we have her blocking script there, so let's copy those values over. So this is the first one, and that's from index 0. And then just copy this blocking script here, copy that, and the value of it was 10 BSV, so 10, 1, 2, 3, 4, 5, 6, 7, 8. And then Alice's wallet import format key in order to lock it, and when we press enter, then it asks for a second one. And so if we bring our Block Explorer up again, we'll just jump into the second transaction. So here's our second transaction ID from, this is the first one that we did, and this time our output is 1. So we're going to use 1 here. Let's copy that stuff over. So copy that, and then 1, and then the script, copy that over, and then the value, if we have a look here, the value is 19 BSV, and then this number here. And so this is the 8 decimal places, so it's 19, and then it's 1, 2, 3, 4, 5, 6, 7, 8. And then we need our unlocking script key here, so that's the change address key, and we'll just paste that in, and then we'll hit enter, and now we're going to be generating a new output UTXO. And so what we'll do is we'll make this Bob's address again. So we'll just say 1, and we'll say the receiver address is Bob. Go. And the number of Satoshis, we'll just stick with our cutting it in half example. So this time we have 39. So let's make it a round number though. So let's say like 15. So 15, 1, 2, 3, 4, 5, 6, 7, 8. And hit enter on that. And then our change address. Instead of reusing any of the addresses we've already used, I just went ahead and generated a new address here. We'll call it Alice Change 2. So we'll just copy that, and we'll use that as our second change address here. So when we press enter, there we go. We get our raw transaction output, and you'll notice it is a little bit larger than the previous ones that we did. Okay, so as I was making this video, I posted the transaction, and I actually got a mandatory script verify failed error code, and I remembered that I didn't actually include a proper SIG hash flag in the program. So just jumping back in here, I'll just show you what I added. So I ended up adding another part of the libsv library, this SIG hash part here. And if we just jump down to the unlocking part, and I had to add the index. So we're looping through these, and we were just unlocking the first one every time. And so what this two parameters do is they tell you which input you're unlocking, and then the SIG hash flag to unlock it. So I had to add those two things. And then once I did that, everything is working the way it should be again. And so if we have a look here, this is our transaction ID that we just generated. So we posted this transaction. We're taking inputs from the two separate UTXOs this time, and then we just have to generate one more block. And if we pull our block explorer back up one more time, we'll just open up a new tab again. There it is. And if we have a look at it, so we have our Coinbase, and then we have our transaction, and you'll see this time we have two inputs. And so we're pulling from two inputs from those two separate transactions. We're combining the value of those inputs, and then we are sending them out to Bob's address again here with 15 BSB, and we're sending the change to this second Alice change address. And yeah, so that's an example, just a quick kind of a quick and dirty example, really basic, just to show you kind of the idea behind this UTXO model and what it means and kind of how it works, and just as a supplement to this chapter, showing you the constituent parts and kind of giving you hopefully a sense of just what's really going on with these transactions, and in particular these standard transactions. And I'll see you in the next chapter.